So let me complete the properties. So last class I think I was telling you about the initial value theorem. Okay, today let us complete the properties. Okay, by starting with the final value theorem. So what was initial value theorem? Given the signal x of n, which is defined only for the positive values of n, that is when the given signal is causal, we can find out its initial value, that is x of 0, by using its z transform x of z by taking the limits as z tending towards infinity. That was initial value theorem. Now today let us continue with that. Now we have final value theorem. So what does this final value theorem say? Like in the previous case, how we found out the initial value x of 0, we are trying to find here the final value x of infinity using the z transform. So let us see its like definition first. So if x of n and x of z form a z transform pair, and the poles of x of z are all inside the unit circle. So what where does this unit circle come into picture? Like I told you, in the z plane you have the ring, right? When you find out the region of convergence, yeah, it is something like that. So if you have x of n and its z transform is x of z, and after finding x of z, if all the poles of this x of z are inside the unit circle, now we'll have a ring here whose radius is 1 and all the poles are inside this unit circle, then the final value of x of n as n tending towards infinity. That means what? You are applying limit to x of n as n tending towards infinity. That means I'll get x of infinity. So this is found out by using the z transform x of z multiplied by z minus 1 by applying the limits as z tending towards 1. So in brief I can say, so using final value theorem, I can find out the final value of x of n, that is x of infinity, provided all the poles of x of z are inside the unit circle. So this signal is also a causal signal. Okay, I can find out x of infinity. For that, I will use its z transform with z minus 1 and apply the limit as z tending towards infinity. Now let us check how am I going to get this. Okay, let us see the proof. Now to prove this, we have taken z transform of two sequences. What are they? One is the z transform of x of n. What is z transform of x of n? I denote that by x of z. Okay, so let me call that as equation number 1. Next, I have taken z transform of x of n plus 1. Now you just remember, what is this x of n plus 1? It is shifted version of x of n. So actually, what should be the z transform of the shifted signal? Already we have studied that, right? So when the signal in the time domain, it gets shifted by some value n minus n naught, its z transform x of z will get multiplied by z power minus n naught. That means what? If the signal is shifted by 1, I should have got, this is for minus n naught. Now here I have taken n plus 1. So if I use this property, actually I should have got x of z into z power 1. But along with this, I am also getting minus z of x of 0, z into x of 0. Why I am getting this extra term? So you should know that this property, what we proved earlier, that was for an signal x of n, which was defined for the complete axis. So your n was varying from minus infinity to plus infinity. The signal what we considered was a double-sided signal. That is, you see your Z transform equations. Your n was varying from minus infinity to plus infinity. That's why we had only this much. But here I am getting this extra term because this is the time shift property we have applied for a signal x of n, which is defined only on the positive values of n, because here x of n is causal signal, right? So for the signal, that is for a signal which is defined only on the positive side, that is only for positive values of n. So I don't have here a double-sided sequence. I have only one-sided sequence. So for that sequence, if you apply the time shift property, you get this extra term. That's all. Okay. So this is the difference. So I get a Z transform of the shifted signal x of n plus 1 equal to z into x of z minus z into x of 0. Let me call this as equation number 2. Now what I do is I'll subtract 1 from 2. Remember what is 1? 1 is z transform of x of n. 2 is z transform of x of n plus 1. So let us see that. So I've subtracted here. So you can see z transform of x of n plus 1 and minus of what? 1. Okay. So z transform of x of n. So we have subtracted. On the right hand side, there's corresponding transforms are subtracted. So what is z transform of x of n plus 1? Z into x of z minus z into x of 0. Like from here, equation number 2. Minus of, what is z transform of x of n? X of z. Okay. Now, for z transform of x of n plus 1, we have written its corresponding expression to find out the z transform. How will you find out the z transform? You have the summation n varying from minus infinity to plus infinity x of n into z power minus n. But what type of signal we have considered here? Causal signal. So the summation becomes n varying from 0 to infinity x of n plus 1 into z power minus n, minus of, what is z transform of x of n? Same, n summation of n varying from 0 to infinity x of n into z power minus n. And here what I have done, this z is taken common. So when you take this z as common, I'm sorry about this. I've taken x of z as common. So when I take x of z as common, from this I get z, and from this I get z minus 1, right? And which is left out, minus z into x of 0. Now let me expand this left hand side for few values. Okay, so if you expand, this is x of n plus 1, right? So when I start from 0, so I get x of 1 into z power 0 is 1, plus. Next, when n is 1, I get x of 2, z power minus 1. When n is 2, I get x of 3, z power minus 2, so on. Okay, this. It goes till infinity. Now minus of, I have expanded this from 0. So I get x of 0 into z power 0, which is 1. Next, x of 1 into z power minus 1 plus so on. So even this minus goes till infinity. On the right hand side, what I have, z minus 1 into x of z minus z into x of 0. Now, what I do, here we have all the negative powers, right? Z power minus 1, z power minus 2. So I can take them to the denominator. So I get x of 1 plus x of 2 divided by z plus x of 3 divided by z square, so on, minus x of 0, x of 1 divided by z minus x of 2 divided by z square, so on. Okay. Now what I do, I apply the limits on both sides such that z tend towards 1. So when z tend towards 1, what is happening? All these z terms become 1. Okay. All these z terms become 1. And on the right hand side, I will leave this quantity, that is limit of z tending towards 1, z minus 1 into x of z. Leaving this, here also z becomes 1, leaving x of 0. Now you think what will happen here? All z's are becoming 1 and this is also 1. So you can just see all the terms are getting cancelled. You can see x of 0 will get cancelled, x of 1 will get cancelled, x of 2 will get cancelled. Similarly, all here whatever terms are there, everything will get cancelled, and one of the term which is on the right hand side, so all will get cancelled, leaving only one term, that is your x of infinity. Okay, so all will cancel except the last term because one extra term is on the right hand side. So you are left only with x of infinity. So I can say x of infinity is equal to. So here all will get cancelled, right? So you are left only with x of infinity. On the right hand side, what I have? Limit of z tending towards 1, z minus 1 into x of z. So that's how we found out what is the final value x of infinity by using x of z into z minus 1 and applying the limits as z tending towards infinity. So this is about the final value theorem. Next is the time expansion. What is actually time expansion? It's nothing but scaling the time, that's all. So I think already you have studied about the various operations on the signals, right? So if you remember, I have just told you. So when you scale the time axis, either the time axis will get compressed or the time axis will get expanded. And how will you expand any signal? This already I told. We expand a signal by inserting extra zeros in between any two samples. Like for example, if I have any x of n, something like this is say 1 and this is 2. Just I am taking an example. This is 2 at 0, 1, 2. Now x of n I have only 3 samples. Now if I want to expand, what I do is in between these two I will insert a 0. So when I insert a 0, so this will be inserted at 1 and this will become at 2. Okay, so if I insert now, what will happen? The number of samples are being expanded. Now the length of the sequence will become 3. That's how we will expand the signal. Okay, so what is happening here in the time expansion property? We are talking about this time expansion. So if you have a signal x of n whose z transform is x of z with ROC equal to R, then if you expand x of n to xk of n, if you expand x of n to xk of n, then z will also get modified to z power k. Z will also get modified to z power k and ROC will become r power 1 over k. Now what is this xk of n? It is expansion of x of n. How it is expanded? See here. Xk of n is equal to x of n by k, x of n by k. That means you are expanding. This is nothing but expansion. And when it will expand? Only when n is an integer multiple of k. Okay, so you get expansion only when n is integer multiple of k. That means what? Say for example, if say n is 2, for example, I am just telling when n is 2, uh, k is 2. Okay, so I get 2 and 2 will get cancelled. So the expanded signal I get x of 1. That is good. So I'll get x of 1. So I have a sample defined that x of 1. Say for example, if n is 3 and k is 2. Now I get x of 1.5. I don't have 1.5 in the discrete time sequence, right? I don't have 1.5. In case of discrete time sequence, all the samples should be defined for the integer values of n. Only for integer values of n. That's what here you can see n and k are not integer. N is not an integer multiple of k. N is 3. So if I divide, I get 1.5, which is not defined. But if I go for integer multiple, like if I take n is equal to 4, then 4 by 2, I get x of 2. So I can define the sample at x of 2. That is, I can insert a sample at x of 2. So that's why we say the expanded for expansion, we should see that n and k, they should be integer multiple. it should be divisible. So n should be an integer multiple of k, and this will become 0 otherwise. That means what? At x of 1.5 I cannot define anything, so it is just 0. I can't define anything. So how are you expanding? As I told you earlier, yes, this is how we are expanding. So xk of n has k minus 1 zeros inserted between successive values of the original signals. So this is what I told. You are inserting zeros between successive values of the original signal. So here 1 and 2 are successive, so you are inserting zeros. And 2 and 2 are successive, you are inserting zeros. Fine. So if you expand the time domain signal in the if you are expanding the discrete time signal in the time domain, the z will also get modified to z power k. So this is about time expansion. So if you expand, your z becomes z power k. That is what we have tried to show here. So you can just see the proof. X of z is equal to summation of n varying from minus infinity to plus infinity x of n into z power minus n. If I change x of n to xk of n, so if I change x of n to xk of n, then what are you doing? You are then instead of z power minus n, it becomes z power k. That's all. There is nothing else to check here. It is just to verify if you are adding samples in between, your z becomes z power k. That's it. Okay. So it's very simple. Next is I have not given the title here. This is the conjugation property. So conjugation property, where do you get conjugate? Whenever the signal is a complex signal, only then you get the conjugation. So what does this tell us? It says that if x of n is a discrete time signal which forms a Z transform pair with x of z with ROC equal to R, then if you are taking Z transform of its conjugate, that means if I take the conjugate of the signal which is in time domain, then you are also taking conjugate of its transform domain. So here if I change x of n to x conjugate of n, even here it becomes x conjugate of z conjugate. There also you are supposed to take the conjugate. Here if you take conjugate, in the transform domain also it has to be the conjugate, x conjugate of z conjugate, but ROC will remain same. Now this results x of z becomes x conjugate of z conjugate only when the signal is complex in nature. Only when the signal is complex in nature. If the signal is real, what will happen? If the signal is real, I don't have any imaginary term, right? If the signal is real, if I take its complex conjugate, the complex conjugate and the signal will be same. Say for example, if I have x of n, say I have 1 minus 2j. If I take its conjugate, what I will get? 1 plus 2j. This is okay. But if I have x of n just 1, which is real, then its conjugate is also same. So that means in the Z transform, if you have any real signal, the Z transform of the original signal and the Z transform of its conjugate will be same. X of Z will be same as x conjugate of Z conjugate if x of n is real. That's it. Now what is the meaning of this? What is the meaning? So it says if x of z has a pole or a 0 at z is equal to z naught, then it should also have a pole or 0 at its complex conjugate, that is z equal to z naught conjugate. That's it. So fine. So it is applicable only for complex signal. So as I told, in the time domain, if you are taking conjugate of the signal, then in the transform domain also, for x of z, you have to take the conjugate. That means if you have a pole of 0 at z is equal to z0, then you should also have a pole of 0 at its complex conjugate. So these are about the various properties of Z transform. Now further, now in the previous classes, you have come across the various examples where we took the different signals and we applied the Z transform to get the X of Z. Normal way. That is by using the equation we have found out the Z transform. Now you have come across the various properties. So these properties will help you in minimizing the number of steps required to find out the Z transform. So in the next we'll see to how to find out the Z transform of various signals by using appropriate properties. So for this you should know very well the properties. So if you know the properties, so within a few steps you can find out the Z transform. So before going to the example, we'll just have a small summary recalling all the properties. Okay. So if x of n and x of z form a Z transform pair, okay, then so what does linearity property say? It says that a into x of n plus b into y of n forms a Z transform pair with a into x of z plus b into y of z. So it's a straightforward time shifting property. So if you shift the signal in the time domain by n naught, the Z transform, the Z transform x of z will get multiplied by z power minus n naught. And scaling in the z domain, if you scale x of z by alpha, the z domain, its corresponding signal in the time domain x of n will get multiplied by alpha power n. Okay. Then time reversal. If you reverse the signal in the time domain, here in the z domain, z becomes inverted. It will become z inverse or 1 over z. Then time expansion. If you expand the signal in the time domain, in the z domain, z becomes z power k. And conjugation. So if you take the complex conjugate of the signal in the time domain, the z domain also, the transform domain, you have to, it results in its complex conjugate. Then if you convolve any two sequences in the time domain, that results in the product of its z corresponding z transforms in the z domain. Then differentiation in the z domain. So if you differentiate the z domain x of z with respect to z and multiply by z, its corresponding time domain signal x of n will get multiplied by n. Then for all this, till differentiation in z domain, the signal considered is a double-sided signal. That is, n varies from minus infinity to plus infinity. And the last two properties, initial value theorem and final value theorem, please keep in mind, we are applying this only for the signals which are defined only on the right hand side, that is causal signals. Okay. If the given signals are causal signal, then the initial value x of 0 is got from x of z, applying the limit as z tending towards infinity. And the final value x of infinity we get by using x of z, the product of x of z into z minus 1, applying the limit as z tend towards infinity. Okay, so this was about the small recap about all the properties. Next, let us take examples. Okay, so here we have to use appropriate properties. Now to use all the appropriate properties, the base signal what we have considered is a step signal. The base signal is a step. So whatever we do all the changes to the step signal. Okay, then we apply the properties and find out the Z transform. Okay, let us see one by one. Yeah. So now the question is common. Find the Z transform of the signals using appropriate properties. So here you'll be using appropriate properties. Okay. Yeah. Let me consider the first signal. X of n is u of minus n. X of n is u of minus n. Now, what is the given signal? As I told you, the reference signal what we take hereafter to solve all the problems is a step signal u of n. Now the example what we have considered is u of minus n. So what is the given signal? It is the reversal of u of n. So now you can think to find out the Z transform of u of minus n, which property can be used? Here you have to use appropriate properties. Which property can be used? Okay. So let me explain this problem. Then after that it will become easy for you. Now I'll start with u of n because the signal given to me is step signal. So I'll start something like this. We all know this already we have found out. The Z transform of u of n is 1 by 1 minus Z inverse, provided Z inverse is less than 1. So I get Z greater than 1 as ROC. Now let me take this signal as our X of n, and this is our X of Z. Fine. Now this form a Z transform pair. Now if this X of n and X of Z form a Z transform pair, okay, u of n and 1 by 1 minus Z inverse form a Z transform pair. Now keeping this as reference, now I have to find out what is the Z transform of u of minus n. Means here I have to substitute u of minus n, which is time reversal. So you already know about the time reversal property. That says, here I have written, just observe. If you reverse the signal in the time domain, in the Z domain, wherever Z is there, it will get inverted. Z becomes Z power minus 1. So keeping this as reference, in the time, now what is our time domain signal? Our time domain signal is u of n. Fine, this is our reference now. So if I reverse u of n to u of minus n, what is its corresponding Z domain signal? 1 by 1 minus Z inverse. Here Z become inverted. Can you see here? Z is becoming 1 by Z. Okay, so I get, after taking Z to the numerator here 1 by Z, so I get this answer, provided Z is, because Z was greater than 1. Now after applying this property, Z became 1 over Z greater than 1 or Z less than 1. So we have found out what is the Z transform of u of minus n without going for a normal approach. We just use the property. So you have reduced the number of steps. Is this clear? Like how you use the property appropriately? So you have to just understand what is the signal given to you. So let me take one more so that you can understand in a better way. Yeah. See here. I have x of n which is equal to a power n into u of n. Means the signal is multiplied with a power n. You can just recall which property can be used here. A power n into u of n. So go back, we'll go to this table. Yeah, yes. Now u of n is our reference, okay? So I have here alpha power n into u of n. So I have to use scaling in the Z domain property. Okay, so a power n into u of n. This I have to find out the Z transform. Now to find this, I'll start from the basic. That is, our reference signal is u of n. So now u of n's Z transform is 1 by 1 minus Z inverse. Now this u of n forms a Z transform pair with 1 by 1 minus Z inverse. Now to this u of n, if I multiply a power n as per our scaling in the Z domain property, it says that if I multiply alpha power n with x of n in the time domain, in the Z domain, its corresponding Z is scaled. Wherever Z is there, it has become Z by alpha. So now you can see, now I took first u of n, whose Z transform is 1 by 1 minus Z inverse. Now to this u of n, I am multiplying a power n. To this u of n, I am multiplying a power n. Now what should happen in the Z domain? Wherever Z is there, that Z will get changed to Z by alpha. That is here alpha is a. So Z by a. So if you simplify, it will become what? Now what I can do is to nullify this negative sign, I'll just multiply this with Z. Okay, 1 into Z becomes Z, 1 into Z becomes Z minus Z by A inverse. So I have Z inverse into Z, 1 A inverse. A inverse inverse. So it becomes Z minus A. So the Z transform of A power n into U of n is Z by Z minus A. So here we used just the property. Otherwise you had to take the summation and do all that. So but here, since we know the property, I have written directly. So you should know the property, which property to be used. Okay, let me go to the next signal. Yeah. Now here I have a power minus n into u of minus n. Now here it's not one property, I have to use more. So I can just on the left hand side, I'll just write what properties we can use. First, we can start with our basic signal u of n and take its Z transform. Next, your u of n is multiplied with a power n. So that is scaling in the Z domain. So I use that property, scaling in the Z domain. Then I'll find out what is the Z transform. After that, n is reversed. So n is reversed means what? Time reversal property. So you have to first go for the reference, then scaling in the Z domain, a power n into u of n. Next, n is changed to minus n, time reversal property. So just started here, see. So what is the Z transform of u of n? So Z transform of u of n is 1 by 1 minus Z inverse. Fine. Next, previous problem, scaling in the Z domain. If u of n is getting multiplied by a power n, then wherever Z is there in the Z domain, that becomes Z by a. And if you simplify, it becomes Z by Z minus a. This previous problem we have solved. Next, I want to find out the Z transform of a power minus n into u of minus 1. So n I am reversing. So here I have to use time reversal property. So a power minus n into u of minus n. So what does time reversal property says? It says that if you are reversing the signal in the time domain, its corresponding Z domain, Z becomes 1 over Z. It is Z inverse. So can you see here? So in this signal, if I reverse n, it is a power minus n into u of minus n. Here, wherever Z is there, it is becoming 1 over Z. 1 by Z divided by 1 by Z minus a. So if you simplify this, I get 1 by 1 minus az. So I have just multiplied the numerator by z and denominator by z for simplification. So z and z cancelled 1. Here z and z will get cancelled 1 minus az. So we have got the answer. Is that clear? So we have used the appropriate properties to find out the Z transform. Yeah. Once again, this is also very simple. You can just see here. So given a power n minus 1 into u of n minus 1. So when you say n minus 1, you can easily understand that it is a shifted signal. So how do you start with? So I can start with the basic reference signal u of n. So what is the z transform of u of n? Next, it is multiplied by a power n, that is scaling in the z domain, a power n into u of n. After that, n is shifted. So it becomes a power n minus 1 into u of n minus 1. So within 2 steps, you can get the answer. So first it is, I have to start with u of n, which is 1 by 1 minus z inverse. Why I didn't write here? Because from the previous problem already you have come to know what is the z transform of a power n into u of n using scaling in the z domain. So already you know about this. So directly I have written here a power n into u of n, z transform is z by z minus a. Now to get the z transform of the given signal, I have to shift n. So time shift property. So what does time shift property says? If you shift the signal in the time domain n minus n naught, its corresponding z domain x of z will get multiplied by z power minus n naught, where n naught is the shift value. So here what is the shift value? 1. So refer these two. Now the z transform of a power n into u of n is z by z minus a. Now if I shift n by n minus 1, its corresponding z transform, this is our z transform, right? So the corresponding z transform is getting multiplied by z power minus 1 because n naught is 1. So I get 1 by z minus a. So within 2 steps you got the answer. So there are some more problems. Okay. So we'll continue in the next class. So I just want everyone to please refer to the properties and come. So otherwise we can't solve the problems by using appropriate properties. So before going to the next few more problems, I just want to know